This video presents the EddySonix Eddy Current Scanner, or ECS, for non-destructive case depth measurement of induction-hardened axle bars and stem shafts. The system is designed to replace routine destructive ECD cut check verification with a trained and validated non-destructive method. The focus is on full-length scanning, multi-frequency eddy current analysis, compensation, validation against microhardness, and long-term calibration-free use. The industrial problem is the routine cut check. OEM protocols require ECD verification at fixed intervals, after coil changes, after part type changes, or after process adjustments. These cut checks are accurate, but each tested part is destroyed. For complex stems, several cross-section and longitudinal measurements may be required. This takes time, material, energy, and laboratory work. Our goal is to run ECS and cut checks in parallel during validation, prove the agreement statistically, and then reduce or eliminate routine destructive checks.
This slide shows a representative shaft geometry. These parts are not simple cylinders. They include splines, shoulders, grooves, and diameter transitions. ECD can be specified at several axial locations, and sometimes at angled locations. In these areas, the eddy current response changes strongly with coil position. This is why fixed point measurement is not enough. ECS uses controlled full-length scanning to keep all control points synchronized with the part geometry. Here is the ECS system overview. The part is clamped between centers, and the coil scans along the axis of the part. During the scan, the system records multi-frequency impedance continuously. Then, the software calculates numerical ECD values at OEM-defined locations. The output includes ECD values, alarms, pass-fail decision, and traceable reports. The complete test cycle is below 30 seconds. The physics is based on the interaction between the hardened case and the softer core. We use several frequencies because one frequency cannot separate all effects. The low frequencies, mainly 5, 10, and 20 Hz, carry the main ECD information and penetrate deeply enough for about 3 to 10 millimeters case depth. The 40 Hz frequency supports the transition region. The higher frequencies, 80, 160, and 320 Hz, are used for surface hardness and compensation of surface effects. Amplitude and phase are interpreted together in the impedance plane.
The scan creates continuous envelopes along the full shaft. This is a key difference from point-only eddy current testing. The system aligns the scanned part with the master reference, then extracts the response at OEM-defined ECD points. Because the coil scans the full length, we also see how the signal behaves before and after each control point. This gives much richer information than a single local reading.
The model is anchored to real destructive data. We start with reference parts, nominal, min, and max case depth levels. These parts are cut-checked, and the true microhardness ECD values are entered at the required locations. ECS then links the multi-frequency envelopes to these ECD values. After training and validation, the model is locked. There is no periodic recalibration. The transition strategy is to compare ECS and cut checks for a validation period. Then replace routine cut checks with ECS verification.
At each inspection point, parts with different case depths form loci in the complex impedance plane. Instead of using raw amplitude or phase alone, the system fits this locus and converts the position into a theta angle. The theta values are normalized, so nominal references are centered near zero. Selected thetas from different frequencies are then combined and mapped to microhardness ECD values. This step converts raw EC amplitude and phase data into a useful ECD estimate. Raw eddy current signals are sensitive to heat code, alloy variation, part temperature, residual magnetism, and surface hardness. Traditional eddy current methods often need recalibration when material batches change. In ECS, the compensation framework separates these unwanted effects from true ECD variation. Material and temperature effects are stabilized, surface effects are corrected using high-frequency data, and local resolution correction restores peaks and valleys near geometry transitions. This is why the trained model remains valid without periodic recalibration, as long as production stays inside the validated range. After validation,
ECS is used at the same verification rhythm as the former cut checks. The trigger can be time interval, induction coil change, part type change, or process adjustment. The difference is that the part is no longer destroyed. The operator gets ECD values, alarms, pass-fail decision, and traceable quality records. Detailed plots are still available for engineering review when needed.
Validation is done by running ECS and cut checks in parallel. For each production part, ECS estimates are compared point by point with microhardness results. Across several part families, we typically observe about 0.15 mm standard deviation and a maximum deviation around 0.3 mm. The validation includes nominal, high case, and low case conditions. This statistical agreement is the basis for reducing or canceling routine destructive cut checks. The transition must be controlled. In a typical case, production parts are collected over several weeks. We scan them with ECS, then cut check them and compare the results. The batch test tool reports RMSE, mean error, correlation, and Bland-Altman agreement. It can also support supervised fine-tuning to reduce bias, RMSE, and standard deviation. However, this is not automatic self-learning. The database is not modified automatically, and the final decision remains under the customer quality protocol.
The practical performance is a typical standard deviation of 0.15 mm, maximum deviation around 0.3 mm, and test time below 30 seconds. Long-term deployments show stable results without periodic recalibration. But there are boundary conditions. A validated reference database is required for each component family. Part orientation, coil selection, and scan parameters must remain controlled. For a new geometry or major process change, a new setup or validation is required. To conclude, ECS transfers destructive microhardness information into non-destructive routine ECD verification. The method combines multi-frequency scanning, Theta modeling, and compensation to handle heat code, temperature, residual magnetism, and surface effects. Once trained and validated, the system operates without periodic recalibration and supports strong reduction or cancellation of routine cut checks. ECS is not presented as a generic eddy current sorter. It is a validated replacement for routine ECD cut check verification. Thank you for your attention.